All right, Mike Watkins, HurricaneTrack.com and HurricaneAnalytics.com. Wanted to take just a few moments here tonight to do a quick update on Dorian. Reconnaissance has been flying in the system pretty much round the clock. They are on literally 4 round-the-clock missions that last about 6 hours each. And aircraft that entered the storm just about 2 hours ago found that Dorian had strengthened to 130 miles per hour. So it is now a dangerous Category 4 hurricane. When you think about what we talked about earlier today about the things that were leading us to believe that it would start to get pretty strong, I don't think that anyone reasonably thought that we would have such a strong intensification in such a short amount of time. In fact, the pressure drop is about 20 millibars since from the time that the last aircraft was there until the new one got there about 6 hours later. The rapid intensification threshold is 24 millibars in 1 day. So in just 6 hours, it's almost there, and we're seeing information coming in from the aircraft that suggests that Dorian probably is stronger than what was reported at 8:30 p.m. tonight. So, and when you look at this image here, you clearly see, I mean, you see the eye is getting rounder, the cloud tops are getting darker, which means that they're colder, which means that they're extending further up in the atmosphere because they're of all the upward vertical motion. And the last thing is, when you look at the satellite presentation, if you see all of these little kind of tentacles or fingers that are reaching out from the storm, that's what we call upper level outflow. And for in a normal thunderstorm during the day at your house, you've got updrafts competing with downdrafts all the time as the conversion from water to ice to gas to water to ice happens in the atmosphere. It releases heat in the eye of the storm. I'm sorry, in your thunderstorm it releases heat, but then you have also outflow, or kind of the exhaust of the process of building a thunderstorm, that sinks and falls into the updrafts, and so you have storms will kill themselves essentially with their outflow, essentially like putting cold water on a boiling in a boiling pot of water. It will stop the process. And so the way tropical cyclones and hurricanes, when they're well organized, combat that is they bring in warm, moist air at the surface, turning counterclockwise, do their thing with physics, and then use the exhaust to take it away from the storm. But it's not dropping it right back on the downdrafts. No, it's dropping them literally hundreds of miles away. So out here, you've got a lot of what was exhaust from the storm getting away from the updrafts down here in the eye, and boom, there you go, rapid intensification. And as long as the storm can maintain that type of structure without any wind shear interfering with it, there's no reason to think that it won't even get a little bit stronger. Now, once they get to a point like this, it almost becomes physically impossible for them to stay super intense. So there are going to be fluctuations in intensity up and down a little bit probably at some point once we understand exactly how strong Dorian is going to get. But regardless of how that plays out, we know it's going to be a powerful hurricane when it comes close to Florida. So let's go ahead and look at the forecast tracks that came out from the global models. This is as of this morning. So when I woke up, essentially this is the map I looked at. Oh my goodness, almost all the models except these two kind of lower, I mean, they're statistical models. They're not really, they're there as a baseline. They don't really use their output much anymore because the dynamical models are better. But everything's coming to Florida, right? So fast forward 12 hours to the models that just finished, let's see, a couple hours, well, yeah, this would be a couple hours ago. Wow. And in 12 hours, we've gone from all the models in Florida to none of the models in Florida, save a couple of them. So when the Hurricane Center saw this, and this is the similar output to what we had this afternoon, we'd have basically 2, 3, 4 runs in a row of the models all over Florida. Now they're way off. Something is different in the atmosphere. But when we look, there's not anything that's obvious that makes the drastic change that we're seeing here. I mean, in some cases, the models are 100 miles away from where they're projecting. So that's why when we say there's uncertainty, we don't know if this is truly the trend, or is this something that in a model run or two, when we put some new observations in, it totally changes the view back to the way it was before. There's no way to know. And so that's why we talk about probability. So instead of saying for sure we know it's going to go here or there, we don't know. But we say the probability of a storm going in a certain direction based off of all the other forecasts that we've ever made is this, and then that's what those numbers represent. So I'll explain that a little bit more. So this is the GFS ensemble, all the members. So one technique for modeling is called ensembling, where you basically change a little bit of each variable to kind of represent uncertainty or things that we don't know in the atmosphere. And we run the same model over and over again with all these different conditions. And in this case, our GFS model, the American forecasting model, does 20 different randomized variables. And that's what's called an ensemble. So then you take the collection of those and you have the ensemble mean or the average. What's interesting about this is that there's the operational GFS, which is strictly one run using all the laws of physics that we know and creating and trying to project what the atmosphere is going to do, which is really hard and takes a lot of computing power. So that model basically shows a track like this on the current. So almost all of the models that are run in the second ensemble exercise don't show that. Not only that, but the ensemble mean here, the average, is right up. Actually, no, that's the previous GFS. The ensemble average actually is out here. But when you, oh no, actually, the ensemble member, the middle point of this kind of spread is there.